This lecture is relevant to fatty acid synthesis. We already looked at beta oxidation, which is relevant to fatty acid oxidation. Now we're going to look into fatty acid synthesis, which takes place in the cytoplasma, while beta oxidation takes place in the mitochondria. So for this slide, I know it is looking very complex and create some anxiety for you to understand it. Let me try my best. Also for to help you to see this whole slide, I'm going to use a highlighter for describing. But no worries, this overview of using a transparency type of slide is only the start off. There will be in the next few slides to come another animation to describe again in terms of the action of fatty acid synthase. So to begin with, it is the acetyl coenzyme A that comes into connecting with the fatty acid synthase. It comes in first time and only one time. After that, more of usage of malonyl CoA for the repeated step in the growing of fatty acid synthesis. So the acetyl coenzyme A will be connected to the ACP site as shown here. Next, the ACP will transfer the acetyl group towards the condensing enzyme as shown here. And after this, since the ACP is now free, it will then grab the malonyl CoA towards it as shown here, and then therefore now both the condensing enzyme and ACP has a group. These two groups, the acetyl as well as the malonyl CoA, will react and form the 3-ketoacyl group as shown here. But before it can react, the malonyl CoA will lose a carbon by forming carbon dioxide. This 3-ketoacyl ACP does not have the shape of the fatty acid yet because of the ketone group. So in order to modify the ketone group, three further steps will take place, and that requires the redundant NADPH, that is a reduction will take place here, okay, and then followed by dehydration causing the formation of double bond, and again another NADPH will be causing the reduction to finally form what looks like a fatty acid, that is acyl ACP. So now from 2 carbon it has formed to 4 carbon, but it doesn't stop there. The acyl ACP will, the acyl group will be transferred to the condensing site, and this will then carry on to form from 4 carbon to become 6 carbon through repeated process of this whole cycle for many more times until it forms the 16 carbon palmityl CoA, covered by the thioesterase, the 8th component of the fatty acid synthase, where it suddenly become alive and does its function, where in the product release. Thioesterase will form the final step where it will release the palmitic acid from the fatty acid synthase. On that will be done as shown here, where assuming the 14 carbon is now formed at the ACP, and then to form the 16 carbon, it will then transfer to the condensing enzyme, and then the palmilanyl CoA will come, just like the way it's done for the extension, and the 14 carbon will be attached to the ACP. But what happens next is there will be no further reattachment of the 16 carbon to condensing enzyme, but instead it will come out catalyzed by thioesterase to form the palmitic acid. So that causes the product release of the palmitic acid by fatty acid synthase. So here the whole process is repeated again with a different animation slide so that you can understand better compared to the other one which uses the old transparency. So we start the explanation by having the fatty acid synthase component ACP, where it is free to react with acetyl coenzyme A to become acetyl ACP. But however, the acetyl ACP will transfer the acetyl group to condensing enzyme. So now ACP is free again, and that will be attached to malonyl CoA to become as shown here. Both the malonyl component as well as the acetyl will react and therefore become longer. The ACP now will have the ketoacyl group, and one carbon of the malonyl will be released out as carbon dioxide. The 3-ketoacyl group does not have the shape that is necessary for acyl or fatty acid. Therefore, further modification needed to be done. This will be done by firstly a reduction using NADPH as shown there, and then a dehydration takes place to form a double bond, and this lastly by another reduction with NADPH will create the acyl group that has the shape and structure of a fatty acid, but it's only 4 carbon. Therefore, this process needs to repeat again, where the acyl group will be moved from ACP to the condensing enzyme. Okay. And now, without any further use of acetyl CoA, but instead the malonyl CoA, the malonyl CoA will react with the growing fatty acid, and this whole process will be repeated until 16 carbon palmityl CoA is being achieved. So here is the summary of what we have achieved. If you look into just one acetyl CoA and 7 malonyl CoA, that is the reaction done by fatty acid synthase, meaning to form palmitate using 14 NADPH. So you get the reaction as shown above. But if you take into account the ACC and also the reaction of fatty acid synthase, therefore you need to realize 8 acetyl CoA will react with 14 NADPH, and 7 acetyl CoA will be converted to become malonyl CoA by using 7 ATP, and due to the two enzyme, finally you will get palmitate as the end product, the 16 carbon palmitate. Something which has been highlighted at the bottom is the issue where the acetyl coenzyme A is mostly found in the mitochondria. However, for the fatty acid synthesis, which so happen in the cytoplasma, so how does the product which is found in acetyl coenzyme A in the mitochondria need to be brought out from mitochondria to the cytoplasma? Because acetyl coenzyme A having the negative charge of phosphate cannot easily penetrate the mitochondria membrane, the lipid bilayer. For that, we need to look into the next slide.